Okay, so we're going to be dealing with electrostatics. Electrostatics is essentially the same thing as static electricity. So that's what you guys would know it as up to this point. I've always thought of static electricity beforehand. I would always think about when I was a kid going to my grandparents' house as a little kid, and there was shag carpeting in one of the rooms. Me and my cousins had nothing else to do because, grandparents didn't speak English, weren't allowed to watch TV, so we'd just rub our feet on the shag carpet and then shock the crap out of each other. Always good fun. And so that is essentially electrostatics. So let's go ahead and kind of dive straight into what electrostatics is. Now, I had you guys watch some videos on electroscopes. Electroscopes are the devices that are insulated, and in fact I can show you a little drawing schematic that I've got of an electroscope. So with an electroscope, the idea here is that you have a conductor material here and a conductor all the way right down the middle, and then a conductor couple of small leaves. So these little things here are these little metallic leaves. Traditionally they are made of gold, but in the classroom, to be honest, we just have aluminum foil as the little leaves. And those leaves would be straight up and down naturally. And then you have a glass insulator and then a rubber stopper up here that's also an insulator. And so what we do is we would take an object that is charged and bring it close to the electroscope and see what happens. So inside of the electroscope, obviously there's protons. The protons are in the nucleus of the atoms, and the electrons are, in their orbital paths. It's not exactly a planet-type orbit, you guys should know that, but they move semi-randomly, although they have certain predictable paths. There's certain probabilities that they'll be in certain locations around the nucleus. And so when we bring some sort of charged object nearby, the protons, the positive charges, are going to stay in their location in the nucleus, and the electrons are going to either move up towards the top or down towards the bottom. So the entire device is called an electroscope. The pieces down here are called leaves, and then the thing at the top is called the penny, the ball at the top. So let me describe the experiment that Benjamin Franklin is really famous for. No, not that one, the other one. So the one that you might know would be the kite and the key. Forget about that one. That one's pretty silly because it's not really probably what he was just trying to prove that lightning was in fact made up of electricity. That's all he was trying to prove. But this is actually the really impressive experiment that he did. He took an electroscope, and then he took a glass rod and a piece of silk. And so he struck the glass rod with the silk and rubbed the two items together. And then he took the glass rod, okay, so let's say that this is the glass rod. He took the glass rod and he brought it fairly close to the electroscope without touching it. And what he noticed was that the leaves at the bottom would separate, okay? So the closer he brought it, the more they would separate. Whoop, not like that. That'd be bad when that happens. So they would separate like this, and then he would pull it away, and they would go back to where they were. Okay. So when he pulls it away, they go back to where they were. And so why does that happen? Well, I don't want to give it away just yet as to which kind of charge a glass rod has. So positive, negative, you don't know which. But I will say that it does have a charge. And depending on which type of charge it has, and in fact, let me take the glass rod out of the way. And let me bring some sort of other material that we do not know the charge of. So I'm going to make another material. Okay. There we go. So this is my other random unknown material that has some sort of charge to it, and we're going to fill that with I don't know. Let's just say it's green, and so here this material, which is charged, comes in proximity. Now let's say that this material is negatively charged. Okay, so it has a surplus of electrons. Let me change a little something here. Okay? And try that again. Okay, so this thing has a surplus of electrons, and we try to bring it over. Anytime, that would be great. Aha, there. And so we grab it and we bring it in proximity. We bring it close. Now what would happen? So opposites attract. Okay, so the negative electrons and the positive protons are attracted to each other. Electrons and other electrons are repelling each other. And so for that reason, when you bring it in proximity, any electrons that are nearby over here they want to get away from the rod. So they would get pushed down. And let me just kind of simplify this by bringing them all the way down here. So they go away from the penny and down towards the bottom of the leaves. And so they're trying to get away from this rod. And so now both of the rods have a negative charge. And so they will separate because there is a charge on them that is the opposite from each other, or it's the same charge, and so they have a repulsive force. Keep in mind that the two leaves will never actually attract towards each other because there is not ever going to be an opposite charge on the two leaves. This is all a conductive material, and so electrons can freely flow from one to the other, and so there will never be a different charge on one of the leaves compared to the other. What if, let me kind of undo everything that I just did for a moment. Okay, and so what if instead of this negative charge, what if instead it was a positive charge? So, okay, so I'm going to bring this up here, and now it's positively charged, and we bring it in proximity. We bring it close to the penny. What would happen? Well, the protons are repelled. Do they move down? No, the protons are in the nucleus. They do not repel. I mean, the whole material, the entire electroscope would get, forced down at that point. So the protons stay in the nucleus, but the electrons will be brought up. So there becomes a surplus at the top of electrons. And at the bottom, there is a surplus of protons. And so that positive charge forces them to separate. And then when you pull the rod away from the electroscope, you will notice that they go back to where they were. Okay? So if you have the same reaction happen whether it's a positive or negative charge, how do you know which one you have? Okay, well, let's do this. Let's take this positively charged object and actually literally touch it. Okay, you actually touch the penny. What happens when you touch the penny? Well, you then have what's known as conduction. Up till now we've been talking about induction, but now because you've touched it and you've allowed an arc to occur, there's an actual transfer of electrons. So conduction occurs when there's a transfer of electrons between the charged object and the object that is touched. So in this case, the electrons are going to transfer over to this rod, okay? Not all of them, but some of them, until the two objects have a similar charge. So let's say that that is enough to produce a similar charge between the two objects. So both objects are positively charged now, but equally so. And the leaves will separate, okay? The leaves will separate, and this time, when you pull this object away, the leaves will stay separated, okay? The leaves will stay separated. So they're going to stay separated like this. Now what you would do is you would take this object and you would recharge it. Okay, so you're going to take the electrons off of this object and make it just as positively charged as it was before. So you take a very positively charged object and you bring it in proximity and not touch it. What would happen? So the electroscope is positively charged. You now bring a highly positively charged object in proximity and you induce a charge. What happens? Well, the leaves are going to separate even more. So the leaves are separated before you even bring this thing in. When you bring it close, the leaves will separate even more. Why is that? Because any electrons that are in the leaves will come up because they are attracted to the positive charge of this object here, and the leaves become even more positively charged than they were before. However, what if you bring a negatively charged object? Okay, so let's do that. Let's make this object negatively charged. So let's bring these electrons over just to represent a negative charge. Obviously you can't actually remove the protons, right? They're still there, but I'm just expressing this as a surplus of electrons compared to protons. So what you do is you now bring this negatively charged object in proximity, and what will happen to these leaves? The whole electroscope is positively charged. The leaves are separated because of that positive charge. So when you bring this object in proximity that is negatively charged, what happens to the leaves? They will relax. Be clear, they never actually attract towards each other. There's never a pull. It's just that they relax. Why do they relax? Because the electrons that are in the electroscope are repelled away from the electrons and the negative charge that is in this object. So they get pushed down to the bottom into the leaves, and it causes the leaves to not be so positively charged anymore, and the leaves will relax. So the closer they get to being neutrally charged, the more relaxed they will get. When I take this object and I pull it away, okay, so I'm going to bring this away, and now the electrons will kind of come back and be more evenly distributed again, which means that the positive charge of the electroscope will be represented by the position of the leaves. So that's how you can tell the difference between two different objects, is you can charge the electroscope with a known charge. Let's say you charge it positively. Now that you know the charge of the electroscope, you can take any other object. If it's a positively charged object, the leaves will separate more. If it's a negatively charged object, the leaves will relax. Okay, let me see if I can just hit the back button a lot to kind of get back to my original position here. That's pretty close. There we go. That's awesome. Okay, great. Okay, so let's get back to the glass rod. Come on, buddy. There we go. Glass rod. Okay, so Benjamin Franklin. He had taken a glass rod and a piece of silk and he rubbed them together. Okay, and through that rubbing, there is a charging by friction that occurs. So you are actually transferring electrons from one object and putting them onto the other. So for as much charge as you gain on one object, you lose that much on the other. To be clear, that is known as the conservation of charge. Okay, that is a very clear and important concept, that it is a physical object that's actually transferring from one object to the other, that electrons are transferring. Let me go over what happened with Benjamin Franklin, because frankly, pun intended, it's actually a pretty cool story. So here's what he did, is that Benjamin Franklin didn't know, like, this was just the very early days of understanding anything with electricity. So what he did, he took the glass rod and rubbed it with silk. And he charged the electroscope, and then he had taken a rubber rod, right, so the leaves were separated, and he would bring the glass rod back in, and the leaves would separate even more. He then took a rubber rod, and he charged it with a fur pelt, with a rabbit fur pelt. And he would take the rubber rod, and the leaves would behave differently. They would relax, okay? They would relax if it would let me do it. There we go. So he was able to recognize that the rubber rod and the glass rod had opposite charges of each other. He had no way of knowing which one was positive and which one is negative, and I'm using serious air quotes here because I hope that you'll recognize why in a minute. Benjamin Franklin assumed that the thing that was flowing was positively charged. And that's an appropriate assumption. There's nothing wrong with that. The problem is that he also assumed that the thing that was becoming positively charged was the glass rod. And in fact, here's the crazy thing. I want you to appreciate this nearly as much as I do. The glass rod, when rubbed with silk, the glass rod is by definition positively charged. I'm not sure if you guys fully understand what that means. Everything else is based off of that fact. A glass rod, when rubbed with silk, is by definition positively charged. The fact that an electron is negative is based off of the fact that a glass rod is positive when charged with silk. If Benjamin Franklin had rubbed the rubber rod with the fur pelt and looked at the rubber rod and said, I am going to make you positively charged. If he had done that, electrons would be positive and protons would be negative. Do you understand that? That's crazy to think about. And you know what? That would have been more correct. Because to this day, we actually lie. You see, the positive objects are not what are flowing. It's the negative objects. Right? Electrons are what do the flowing. And so when we talk about the flow of electrons, that's the flow in a negative direction, isn't it? Does that not make things confusing? Heck yeah, it does, especially when we start talking about electricity. Because when we talk about electricity, we talk about the flow of charge, not the flow of electrons. We talk about the conventional, the by rule flow, positive flow of electricity, this idea of electricity, when there is no actual thing flowing in that direction. Instead, it's the electrons flowing in the opposite direction. And the whole reason why we have to do that is because Benjamin Franklin basically flipped a coin and decided which thing was going to be positive and negative. He just happened to be wrong. Whoops! And we still deal with it to this day. So it's a little, very interesting tidbit of history info on why we still deal with that issue and why it is that protons are positive and electrons are negative. Remember that protons and electrons have the exact same amount of charge. They don't have the same mass, not even close, but the amount of charge that they have is the same. So the charge refers to how much force, how much electrostatic force they will push on an object. So it turns out that a glass rod is positively charged, and it is that way because by definition it's been defined that way, and a rubber rod is negatively charged. Okay? So when we take a glass rod and we bring it in proximity, let me move this one out of the way. So we take a glass rod and bring it in proximity. The electrons are moving towards the top of the electroscope, and the electroscope, the leaves of the electroscope become positively charged and they separate. Okay? Okay. So let's kind of talk a little bit about conducting versus insulating materials. So here I have this grid of what essentially represents protons and electrons. And then over here I have one solid object that is positively charged. It effectively has virtually no electrons to speak of. And you're like, if it doesn't have any electrons, then how is there a chemical bond between the object to make it a solid object? Well, if you are questioning that, then you would be smart to think about it, but don't do that, because you'd be messing up my system here, okay? So here we have an object that is neutrally charged, and here's an object that is positively charged. And so what I'm going to do is I'm going to be a little bit more detailed about what happens with this induced charge. We're going to bring this object, this positively charged object, and we are going to bring it in proximity to the neutral object. And what happens? Well, this happens, right? Look, right? Let me do that again. So the object is far away, everything's neutral. We bring the positive object close, and the positive protons and the negative electrons are attracted to each other. Now remember that the protons stay in place. They're in the nucleus. But the electrons are attracted towards the protons, and they will kind of gravitate into that direction. And so they kind of slide over into that direction. So, why is it that that happens, and why is it that all of the electrons are moving over together in this sort of matrix? Okay, well, hold on to that thought. I'm going to show you something different before we answer that. Let me show you something slightly different. In this case, I have this positively charged object, and I'm going to bring it in proximity to this object. This is a different type of object. Watch, it's going to be different. In this case, again, the electrons are attracted to the protons. So what will happen? The electrons will come over. But rather than all of the electrons coming over in one even split and they shift over, instead, electrons come from all over this material to come to the near side, or as close as they can at least. And you'll notice that we have a buildup of electrons here, maybe even a few over here. And so there's a buildup of electrons on this near side, and there's less electrons on the far side. So it is a charged object now. But you see how these two events are different. This one versus the other. Okay? This one versus this. So my question to you is, which one is a conductor and which one is an insulator? I hope that you should recognize that they are in fact different. Okay, they are different. So which one is a conductor and which one is an insulator? Okay, so which one is the insulator and which one is the conductor? I would certainly express that this one here is the insulator. Why is it an insulator? It's an insulator because each electron is bound to its respective nucleus, right? So no electron is actually completely leaving the atom altogether. So in fact, if you think about atomic theory, you know that electrons will, kind of float around the nucleus in some sort of way. We don't really know exactly how, because it's not actually orbits, but we do know that you can predict the probability of an electron being here versus there. But when this object comes in proximity, what happens is it changes that electron orbital path a little bit. And so it makes it so that way the electron spends more time on the near side of the atom, right? And if it spends more time on the near side of the atom, then we're going to have a surface here that is negatively charged, and then we're going to have a surface on the opposite side that's positively charged. Okay, this is an insulator. Versus this one, the electrons are able to fairly freely move. They are not bound to each respective atom. They're able to move fairly freely through the material, and the electrons are able to conduct through the material and get to the near side. Okay, conductor versus insulator. Let me go ahead and hit the back button just 10,000 times so that way I can get everything back to its original position, and that'll work pretty well. Okay. So with an insulator, you can get in proximity, you can touch it, and then when you pull away, you're going to have taken some of the electrons. So this object will be negatively charged now, right? Or, excuse me, positively charged. Please excuse me for that mistake. So they are both going to be positively charged. But with an insulator typically is not going to stay positively charged. Why? Because you as a person are probably holding the object, and you will donate some of your electrons to this material just by the fact that you're holding it. And so because you have such a large bank of electrons, because you have a large body compared to this probably small material that you're working with, you are going to give electrons to this metal material as it loses them. So it's never really going to gain a large amount of positive charge. It is unlikely to do so. It's not impossible, it's just highly, highly unlikely. If it doesn't gain electrons from you, it's probably going to gain electrons from the air around it. Because as a conductor, it's so much so is willing to gain and accept electrons from anything around it. Yes, it's willing to give electrons to the positively charged object that touched it, but it's also just as willing to take electrons from the air around it as well as it does so. Versus, as I undo what I just did, versus the insulator, what you can do is you can actually take a very positively charged object and maybe take a few of the electrons, right? A few electrons might come off, and I can't do that since I have them all kind of structured together. But if you can stick with me here on that idea, if this was an insulator, maybe I could take a few of the electrons away, and I would make it positively charged. And when I take this object and pull away, it'll stay positively charged because it resists accepting or donating electrons. So if I'm able to take an insulator and I'm able to forcibly make it charged, it's going to probably stay that way for a while. Case in point, a balloon. Take a balloon and what do? Right? You rub it on your head, right? And then you stick it on somebody. You ever done that? Right? You take a balloon and then maybe it sticks on you, or if you take a balloon, rub it. Right? What's happening in that moment? You are taking a balloon and you are actually rubbing electrons off of it. You're taking the electrons, and I think you're taking electrons off of it or putting them on. Let me actually double check on that real quick. Okay, so after a quick little look, I was able to realize I was initially wrong. The balloon becomes negatively charged, just like the rubber rod. That's what made me think of it. And so you rub that thing on your hair, and the balloon gains electrons from you. And in fact, let me take a bank of electrons. Maybe I can do that. Maybe I can draw some electrons real quickly to actually represent that a little bit better. So just give me a quick moment to do that. So I'm gonna take some electrons and just kind of make a field of electrons real quickly. See, this is how I do this. Lots of copying and pasting. Yeah, I see it compounds. Once I do the first couple, it becomes easy. And that should be enough there. All right, so I've got my bank of electrons. And so here's my balloon. It is negatively charged, and I bring it in proximity to this neutrally charged object, which is an insulator. What is this object? Well, how about you or your friend, right? So you take the balloon and you stick it on your friend. Your friend is an insulator, right? Your sweater and the human body is mostly an insulator. And so what happens is the electrons will be pushed away. So the far side becomes negatively charged, and the near side becomes positively charged. Now, the near side, which is now positively charged, and this balloon are now attracted to each other. And so it sticks. Boom, it sticks. And it's going to stay that way a while, isn't it? But eventually the balloon falls off. Why? Because eventually a few electrons from the balloon will start to transfer over to the body. And once that happens, they will become the same charge, and it will just fall off. And so that's why balloons stick to objects that initially aren't really charged. Okay, so we actually covered a lot of content. I'm going to go back to my PowerPoint, and I'm going to fill in the gaps where needed, because I've covered a lot of stuff. So charging happens with rubbing, okay? And so that's how you can forcibly strip electrons off of objects. Typically we do that with insulating materials like glass and rubber. Charge is conserved because charge is made up of whole numbers of electrons. Please understand, you can't have half an electron, right? Like, how many people are in the room? It's like 7.5. Wait, what? Right? You'd be really questioning things if that was somebody's answer. And that's how charge works, right? So it's whole number of electrons. And just kind of going through the idea of how electricity essentially fundamentally works. All right, trying to work on this. There we go. Water is a polar molecule. Why is it polar? Because you guys should know that there is one hydrogen and one electron in each hydrogen atom, right? And so the hydrogen's proton stays in the middle of the atom. What happens to the electron? Well, the electron winds up staying over here because it's involved in that bond with the oxygen, right? Which means that if you were over here by this positive plus sign here, right? If you were standing here, like you've shrunk yourself, honey, I've shrunk myself, right? And so here you are standing here, and you look at the atom, you're going to see the proton pretty close to you, and the electron is going to be fairly far from you. So in your perspective, it's going to be a positively charged molecule. For the same reason, from over here, you're going to have more electrons closer to you, so it's going to look negatively charged to you. And what winds up being pretty neat about this process is that with water, this is why water is a material that has a pretty good surface tension, cohesive forces, and it's why water beads off of your arm in the shower, right? You ever stick your arm out, you can see like water, kind of beading off of the bottom of your hand and kind of drips off of you. And so what happens is when you put two water molecules together, let's say that, the two water molecules go together, if I have the two negative sides at my fingers, well, opposites attract. So one of two things is going to happen. Either the two water molecules repel away from each other, or one molecule will rotate, right? It'll rotate to where then the negative and positive sides are now attracted to each other. And so the rotation part is easier to do. And that's what's essentially always going to happen. Conductors versus insulators, and then semiconductors. So I've talked about insulators and conductors. So insulators would be wood and glass and rubber. Those are probably the big three that are really obvious. And then conductors would be any sort of metal generally. And there's a really big misunderstanding that water is a conductor. It's technically not. Water itself is actually an insulator. It is the impurities inside of the water that is the conductor. It's just that the water happens to be the pathway, or it's the holding, the thing that holds all the impurities. So it's all the salts that are actually the conductor inside of water. So salt water is more of a conductor than fresh water, for example. By the way, there's a really good connection between thermal conductivity and electrical conductivity. So a material that allows heat to transfer through it very quickly also typically will allow electricity and electrons to flow through it very easily. What about semiconductors though? So semiconductors are materials that aren't really necessarily insulators or conductors all the time. It's not that they're in between, it's that they're one or the other depending on the scenario. So semiconductors typically are going to be insulators at normal room temperatures and things like that. So silicon, for example, is a very good semiconductor. It is an insulator unless you put it in an electric field. So typically there's two factors that can affect a semiconductor, either temperature or electric field. So let's say, for example, you have a circuit where there's two different pathways. Okay, so electrons can either go this way or they can go this way. Okay, and let's say that you have two different materials between the two different pathways. One is, a decent conductor, and then the other one is a semiconductor. Or even if they're both semiconductors, you can make it so that way electricity is flowing one way, but then you put one of the semiconductors in an electric field, and all of a sudden it goes from being an insulator to a really good conductor. Now electricity is going to be flowing this way. And that is effectively how circuits work. Like, that's the bottom line, is that you're now allowing a computer to decide, am I going to let electricity flow this way, or am I going to let electricity flow this way? Okay? And you do that in sequences, and now you start getting like code, and you start getting binary information going across because it's happening in sequences, and that is the fundamentals behind circuitry, is that you are basically allowing current to flow one way versus another, and being able to have something that makes that decision as to when and why that happens. Alright, so I've talked about charging, and I can probably skip right through most of these, except for maybe this one. So in this case, charging through induction. So I had a video for you guys that demonstrated this, if I can maybe go through this again a little bit. So let me demonstrate it with this. So let's say that you bring a positively charged object right in proximity, and some of the electrons are going to build up on the near side trying to get closer to this positively charged object, right? So I'm going to just grab a few of these electrons and bring them on the near side, okay? Now, this object is not going to touch this object, right? There is not going to be conduction between these two objects. But the electrons do want to go towards the positive object, and they want to get out of this object. The electrons are like, wait, I want to be over here way more, and I don't want to be here. So you can take advantage of that process by taking a third object, which I am going to just say is the ground, okay? Okay, it's ground. It's grounded, it's not in trouble. It's a different kind of grounded. And so we're going to take a wire of some kind, and we're going to connect that wire to the ground, or whatever it might be. And so since the electrons want to get out of this material so badly, they will go through the wire and come into this material. Right? So they're going to leave this material, even though the charged object never actually touched the neutral object. It's going to push the electrons out and through because they want to get closer to this object, but the only way they can do that is by going through this material here. And so then you can take the wire away, and this is going to stay positively charged. So this is grounding through induction. You're like, why isn't it conduction since you actually touched it? The reason being is that you never touched it with the charged object, okay? The charged object induced a charge, and then you touched it with something that was neutral. And basically, the grounding basically means, by the way, rather than the literal ground doing it, it could have been you. In fact, what if after this was done, right? Let's take the ground out of the picture. What if after this was done, you come over and you're like, oh, look at that material, and you touch it, right? So you're gonna reach out your arm, and you maybe take a metallic stick and you touch the object, and you're gonna allow electrons to flow from one object to the other. And so in this case, it wants electrons, and you have electrons in your body, right? So it would take the electrons from your body, and they would flow into that. Now, I'm assuming that this object isn't so large, but you are large in comparison. So if it's an electroscope, for example, you are so large, you might as well be the ground at that time, right? So you've effectively grounded the object. It didn't actually touch ground, it touched you, but you can still say it's effectively grounded because you have such a large bank of electrons to either donate or receive. You've effectively made it really close to neutral. So that is an example of inducing charge onto an object. Okay. I talked about all this stuff, so I get to skip through all that because this is where I want to get to. This is Coulomb's law. F equals K times Q1 Q2 over R squared. This equation should look really, 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 really familiar to you. The letters are different, but the form is the same. Please notice that. F equals K times Q1 Q2 over R squared. Does the form look familiar? You should have had an equation before that had force on one side, R squared in the denominator on the other side, and then some other similarly structured letters as well. If you remember, now in fact let me write it. Let me write it here. Let me just make a new thing. Okay, so if you remember before, it was that the force of gravity was equal to big G times m1, m2 over r squared, right? I would hope that's familiar, where this is the mass of one object, the mass of the other, the distance between them, and then the gravitational constant, and that's the force of gravity between two planetary objects, or maybe between the planet and you. Well, this is very, very similar. So the electrostatic force between two objects is equal to K times Q1, Q2 over r squared, the distance between the two objects. Instead of mass, it's charge. Q is charge. By the way, Q can be represented with a lowercase q. I'll get into the specifics why in a little bit. So this is sort of the equivalent of mass in this case, right? It should make sense that the more charge, the more force. And so it compounds. Therefore, it makes sense that they would be multiplied by each other. Since it is a three-dimensional radiant field force, it should make sense that it should dissipate at the square of the distance. So it should make sense that it should be over r squared. And then this, remember before I had described this one as being sort of like a conversion factor? But that's what K is. It effectively is just a conversion factor. But if you remember that G was 6 point, oh, that's an ugly 6. I have not made it look better. I'm not even going to bother erasing it. I need to remember my mistake. 6.67. What is wrong with me? 6.67 times 10 to the negative 11th, right? That's the value of big G. So that, because it's to the negative 11th, it shows that it is a very, very small number, right? The force of gravity is very, very small. It's a very small, weak force. So what is K? How does that compare? K is equal to 9 times 10 to the 9th. Again, I'm not even going to concern myself with the units. That's a big number. Electrostatic forces are very large forces in comparison to gravitational forces. It is extremely different in that way. So the bottom line is just like planetary bodies, where you have one object here and one object here, and we want to know the force between them. Well, it's the same idea. It's just that instead of them being big planetary objects, we're talking about one little object and one other little object. We have Q1, charge 1, and we have Q2, charge 2. And we want to know what the force is between them, where the distance between them is r. The charge is measured in coulombs, okay? It's measured in coulombs. So we often, the charge that builds up on objects, we often will express charge in terms of microcoulombs, okay? So microcoulombs, right? So this is micro, it's times 10 to the negative 6th. That's what a micro is. Microcoulomb would be times 10 to the negative 6 coulombs. So a coulomb would be an amount of charge. Okay, so let's see if we can kind of go back and continue on a little bit here. Okay, so we know the force between two charges. I had expressed that capital Q and lowercase q both represents charge, but there is a bit of a caveat there that I'll get into in a minute. Remember that like charges repel and opposite charges will attract. Okay? Positives repel, negatives repel, positive and negative attract. If you look at the textbook, and the way that it is often done is that the annotation is expressed like this, where the force acting on object 2 from, the force acting on object 1 from or due to object 2. Okay, so F12 would be that expression. Now, to be honest, I often would express it with just one letter, and I'll just be consistent as the way I go about it. So here is that value of K. This is expressing it as 8.988. It's 9. It rounds off to 9. It's totally fine. Just use 9. So it's 9 times 10 to the 9th. Here are the units. It's newtons times meters squared over coulomb squared. And it's, again, I don't really pay too much close attention to it. Microcoulombs times 10 to the negative 6th. The charge of an electron is a very small amount. Should you memorize that number? You don't have to. It is on the AP test equation sheet. However, it is something that would be, it gets used enough to where it's probably worthwhile to kind of like remember it, or at least have it be familiar. So the charge of an electron is 1.602 times 10 to the negative 19th coulombs. It's very small. This is why electric charge is quantized. It is in whole numbers of this number, if that makes any sense. I guess it's not technically a whole number, but you know what I mean, right? So it is in multiples of this number. That also goes for protons. Protons have the exact same amount of charge. So let's say, and this actually trips people up way more than it ever should. Listen to me on this. If a question were to ask you, what is the force between two protons that is a certain distance apart? And you're like, well, I don't know what the charge of a proton is. It doesn't say it on this equation sheet. It tells me the charge of an electron, but it doesn't tell me the charge of a proton. They're the same! Okay? So just remember that, okay? Please remember that the charge of an electron and proton are the same. So this represents the charge of an electron and proton. It's just that it's usually not stated as the charge of a proton. You should already know that. This is where things are a little bit annoying in terms of being unnecessarily mathy for us. All I'm going to say here is that the value of K can be essentially converted into what's known as the permittivity of free space. This is epsilon naught. Epsilon naught is the permittivity of free space. It basically is a different representation of the value of K. The reason behind it, I kind of had a similar explanation when we did some simple harmonic motion stuff, where it just comes down to a lot of physicists will prefer to express the equation in this form, because I think that it, for the math end of things, as you start to really get into things, it starts to make more sense in that way. But for us, all that we need to know is that there's a direct conversion between K and epsilon naught. Okay? There really isn't any further understanding that needs to be done more than that. Okay? And you guys know that I hate to kind of do that sort of thing, but it's just one of those things that's not worth going into more. Maybe in AP Physics 2, maybe, but not for us. Okay? So I'm going to move on. Just know that there's that conversion. Okay. We're going to go back to your favorite topic ever. Vector addition. Okay? So, here I was talking about the forces between two charges. Oh, wait a minute. Is there only two charges in the entire world? No, there's more than that. So let's take a look. Okay, so if I have three charges, not two, but three charges. Okay, here we go. So we have charge 1. So I'm going to put Q1 over here, and let's say I put Q2 over here. Okay? And I'm going to put a little dot to represent each of the charges. Okay? So those points, and in fact, what if I did this? What if I color coordinated them in some way? So I'm going to make this one blue, and I'm going to make this one some other color. Let's make it like a dark red. Sounds great. And then I'm going to have a third charge. And typically speaking, what we would express is that the third charge, I'm going to make the third charge purple. What if I put a third charge somewhere over here? Okay? Now, that third charge, I could call it Q3. But instead, I'm going to give it a different name, because my purposes of having that third charge often are going to be for the purposes of figuring out how much force would there be on some sort of potential charge at this location. So in fact, let me just kind of take this charge away, and I'm going to put like a little tiny dot in its same spot, boop, right there. And that little dot just represents a location, not an actual object. So at that location, how much force would there be on some other random charge if I were to put it there? So what I'm going to do is I'm going to take an extremely small test charge. I'm going to put it there. Now that test charge is going to serve the purpose of only kind of putting the charge there solely for the purpose of figuring out how much force there would be if I were to actually put it there. I know that seems a little bit meta, right? And so what we do is we call it a test charge. And so for that reason, I'm going to express it with a lowercase q. So it's still a charge. It's just that it's a test charge that I've put there solely for the purpose of figuring out what the electric field is like at that location. Or perhaps I want to figure out what the acceleration of any charge would be at that location of some various sizes. So here, maybe what I would do is I would say, okay, how much force is going to be on my test charge, where all charges have a charge of 1 microcoulomb. So this one is 1 microcoulomb, this one is 1 microcoulomb, and the test charge is also 1 microcoulomb. Okay? Now, a couple things I need to say. First off, test charges. Test charges are always as small as they can be. 1 microcoulomb is probably a fairly standard thing. Sometimes 1 nanocoulomb, it kind of depends. By the way, nano is times 10 to the negative, 9th? Pico is times 10 to the negative 12th, right? So those are a couple of things that you might start to hear. You don't usually hear that, but with charges, sometimes you do hear those numbers. This is also a very important point. Test charges are always, 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 always positive. A test charge is always positive. These charges, let's go ahead and say that they're positive. That's fine. Let's make them positive. If they weren't, I could put a negative in front of them just to express that it is in fact a negative charge, but let's make them all positive. I want to know what the force would be on this charge due to the other two charges. Now, you might say, now wait a minute, this object has just as much charge as the other ones. Isn't this object going to apply a force onto Q1 and force it in that direction? Yes, but we're going to pretend like that's not true. We're going to pretend as if Q1 and Q2 are stationary, somehow fixed in position. And the only one that has the ability to move is going to be little q. Okay? We're going to treat it as if that's the only one that has the ability to move. And so what we would do is we would say, okay, the force acting on the test charge due to object 1, okay, so notice how I'm personally, this is how the text would do it. They would say, okay, what's the force acting on the test charge due to object 1, right, to charge 1. But I don't even bother with that other annotation. So I'm just going to say, okay, so the force due to object 1 is equal to K times Q1 times the little q over r squared, where r squared is the distance between object 1 and little q, right? So I'm going to say that, let me switch colors here. I'm going to say that this distance here is r1. Let me also say that the distance here is just, let me just say that it's r with no subscript, just to kind of keep things separate. I'm just going to give that a value of r with no subscript. Okay, now I'm going to say that the force from object 2 acting on the test charge is equal to K times Q2. By the way, I never put that Q1 there, did I? Whoops, my bad. Q2 times the little q over R2, where R2 is the distance between those two charges. Now, if you're paying any close attention here, you would notice that this is a triangle that's developing, right? Right? So we have a triangle here. Boop. Where R2 R2 is the hypotenuse of that triangle, right? Where R1 and R are the legs of the triangle. You with me? So what you would have to do is figure out these forces. This force, right, the force from object 1, this force, sorry, I don't want to mess up my color coordination that I've kind of got going on here. This force here, in fact, what I should do is since I'm doing color coordination, I should make this red in color. That's better. Okay, so the force from object 1, you should recognize that that force is, let me keep the same color, that is going to apply a force in this direction, right? That's from Q1. Q1 is going to apply a force in that direction. Q2 is going to apply a force down and to the right. When you figure out the value of these forces, in fact, if I'm going to actually truly keep my color coordination, I suppose this one should be blue, shouldn't it? There. When you figure out the value of these forces, do you recognize to find the net force, you're going to have to do some vector addition? Right? You with me on that? So this one here, is acting completely in the x direction. This one here has components that are both in the x and y direction. No, I didn't even mean to do that. My bad. Let me see if I can break that down. So it has components both in the x and in the y direction. So you're going to have to add up the x's, add up the y's, and then find the hypotenuse of the resultant, right? Remember how to do that, right? X and y coordinates. You have the force from object 1 in the x direction. That would be whatever this value here is. In the y direction, it would be 0, right? There is no vertical part to this force for object 1, or from charge 1. For the second one, it has both a positive x, whatever it is, it's a positive value, right? And then it has a negative value. I don't know the numbers, but it's no big deal. It has some sort of negative value because it's going down. You'd have to add those up, the x's and y's, you add them up, and then you make a new triangle and find the hypotenuse of that triangle. Just a little bit of recollection of vector addition. You might want to go back and re-watch my vector addition video if you need that refresher, okay? Electric field. Electric field is force per charge. The electric field is force per charge, and so it's a little q because what you're doing is you're putting that test charge there just for the purposes of trying to figure out how much force there would be at that location. Now, since electric field is force per charge, okay, since electric field is force per charge, then let's express it like this. So we have electric field is equal to force per charge. However, wait a minute. Remember, force is equal to K times Q1 times Q2 over R squared. But since we're using a test charge, typically what we will do is rather than saying Q2, instead we will say little q, right? We will instead say that Q2 is going to be the test charge. So what I'm going to do is I'm going to take this and I'm going to substitute that in for the force. So let's do that. So I'm going to do that substitution. So the force is K times Q1 times little q over R squared, and that whole thing is over Q, which means that the Q cancels and it's left with K times Q1 over R squared, right? Which is the equation that I think I have on my next slide. So that is why we have a test charge that is a theoretical tiny charge, because it winds up canceling out anyway. We just want to figure out what the force would be on a theoretical object at that location. All right, just kind of, you know what, I'm going to wind up just kind of drawing out the rest of this anyway. Okay, so let's say I have two charges that are in isolation from one another. Okay, so they are not even close to each other. I'm just going to bring them really far apart. They're so far apart that they have no effect on the other. So remember that a test charge is always, always by definition positive. So if I were to put a test charge right there, my test charge Q, how much force would be on that object and in what direction would the force be? Well, the force would be in that direction, wouldn't it? Because they're both positively charged. And so I would draw an electric field going away from this positively charged object, going out in all directions like this, because that is what would happen to any positively charged object put anywhere around it, is it would be forced away. So the electric field basically shows the force that would be acting on any object put in that location. And so if I were to then take this test charge and bring it over here, it is a positive test charge. So what would happen? There would be a force acting towards this negative charge. And so the electric field should be going in towards this negatively charged object from all directions. Okay? Does that make sense? I hope so. But what if we instead don't just have monopoles, right? These are monopoles. They have one charge. But what if instead we bring the two charges together? They are no longer in isolation. So they are now actually so close to each other to where you have to consider what happens to the electric field for the two. So what happens? Well, a test charge that's put in between will want to go away from this and towards that. It'll want to go away from here, but you know what it's going to do? Is it's going to loop around, kind of like that. And it's going to loop around kind of like that. And it makes this sort of pattern. This, again, remember, is the electric field. It represents the direction of the force at any location around these charges. It's probably not the best looking sort of thing that I've ever done, but you get the idea, I hope. Now remember that it just represents the direction of the force, not the direction that it actually is moving. So let's say that I were to put an object right here, and the object would start to accelerate in that direction at that moment in time. But as it picks up speed, remember that it has momentum, it has inertia, it has mass. So if this positively charged object goes this way, now the force acting on it will be in sort of that direction, right? Well, it's going to make it sort of have a curved path out this way. It's not going to actually flow in that direction. That's just the direction of the force acting on it, okay? So just be clear on that. If you have charged plates, the electric field between the two charged plates will be fairly even and uniform, except for the very ends, but that's pretty negligible. And so if you think about the potential energy of the system, there's more potential energy here for a positively charged object than here, right? It would take energy to move a charge towards the positive plate. And then you let go of it and it wants to release and go down this way. And, oh, here we go. This is a good one. So if I have in fact, let me draw this out. I think I have something I can do here. Here we go. So let's say that I put a positively charged object inside of a hollow metal sphere. And in fact, wait, hold on. Before I do that, I'm going to put in a test charge. I'm going to put a test charge here. Okay, now I'm going to take this object. I'm going to move things around a little bit. So I'm going to move this guy out of the way. Okay, he's out of the picture for a moment. In fact, I'm just going to move him as far off as I can for the moment. So there is an electric field around this positive charge, and the test charge would feel some amount of force because of it. Now the question is, how much would that force change if I were to take this hollow metal sphere and put it around the charge? Would the electric field that the test charge feels be different? And the answer is no. And here's why. The electrons would all gravitate towards the inside of the sphere, right? They would do that until the area is as neutralized in the middle as much as possible. In fact, the electric field on the inside of the sphere is very minimal at this point. But on the outside, the electric field, right, you see how that they're close to the positive charges? The electric field would shift within the metal sphere until the electric field on the outside is the same as it was before. Let me go through another interesting example. Let me kind of undo some of my changes. Oh, I went too far. Okay. So what if I had it the opposite way around? What if I had a positive charge here, and I had a, let me move this off to the side again, and I had a test charge that was right here, okay? Now, before I had the test charge outside of the sphere, but what if now I put the test charge inside of the sphere, right? You know that before I do it, the test charge is experiencing some amount of electric field, okay, due to this charge. When I take this hollow metal sphere and I put it around the test charge, what would happen? The electrons would go towards that positive charge as much as possible until it just totally neutralizes the charge. So as far as what is being experienced inside of the sphere, it would be neutral. If you were over here, right, if you were a test charge over here, that'd be different. You'd be experiencing a positively charged electric field. But inside, nope, no electric field at all. Which is why, during a lightning storm, you want to be inside of a hollow metal sphere. It gets struck with lightning. Doesn't matter. The electrons build up along the outside, and it winds up producing an electric field that pushes outwards because all the electrons are repelling each other. So it pushes the electric field out and away, and you are protected on the inside of a metal sphere. And you're like, during a lightning storm, where the heck am I going to get into a metal sphere? Oh, I don't know. Maybe the one you drive? It's a big hollow metal object. They're perfectly safe in a lightning storm, even if they get hit by lightning. People think that it's because of the rubber tires. No, it has nothing to do with rubber tires. Planes, airplanes get struck by lightning all the time, and it is known as a Faraday cage. It produces an electric field that pushes outwards, and you're safe on the inside. You'd be safe in virtually any car, except for like a Corvette, because they're fiberglass, not metal. You just have to hope that you can outdrive the storm. All right, so I think that's going to be pretty much about it. There's other issues like flux, but we don't need to get into that stuff. And that is a lot of content that I've given you guys. But with this topic, the way I look at it with AP Physics is we want to get through the electrostatic stuff so that we have an understanding conceptually, a little bit of math there, but most of it is that we have enough understanding so that way when you move over to circuits, you can really be able to apply it there. That's the importance. So with that, I'm going to end the video here. So if you're watching as a video, hey, that's out. Peace out. We'll end it here.